We continue our exploration of descriptive statistics. We've already discussed different ways of talking about where numerical data is centered. We've talked about ways of talking about its spread or variation. This section focuses on how to talk about how data values relate to one another in terms of distances and so on. And then we're going to look at a graph that helps us explore some of the characteristics of data: center, spread, outliers, and shape, called a box plot. We're going to spend quite a bit of time in this section talking about what a z-score represents, not only how to calculate it, but how to interpret it and how to use it to answer some questions about whether data values are to be expected or whether they are extreme enough for us to consider them to be significant. We're also going to talk about percentiles, quartiles, and how to construct a box plot. Let's start with the definition of a z-score. A z-score is also known as a standard score or a standardized score, and it is the number of standard deviations that a specific data value, which we'll call x, falls from the mean. So it is a distance. It is a distance from where the data value is and where the mean of the data set is. Now that distance is calculated in standard deviation units. Therefore, let's look at how the z-score is calculated. We have two formulas that are essentially the same. This first formula represents a z-score coming from sample data. You see here that we have the sample mean x bar and the sample standard deviation s. The second formula is how to calculate a z-score when we have data from an entire population. You see that because we have the label mu for the population mean and the label of sigma for the population standard deviation. But essentially both formulas are doing the same thing. They're looking at how far a data value is from the mean. So this is one value, a specific data value in the set x, subtracting the mean from that, so that's how far the two are from each other. But then we're dividing that by the standard deviation, and so that distance is given to us in terms of how many standard deviations the distance represents. When we're working with z-scores, we will always round those calculations to 2 decimal places, regardless of how far the data values went. So z-scores such as 2.31 would be considered, and that is so that we can use the accompanying tables that have all of the z-score calculations out to 2 decimal places. We'll talk about those later when we look at the formulas and charts. Let's look at some properties of z-scores. First, a z-score, as I said earlier, counts the number of standard deviations that any specific data value x falls from the mean, either above the mean because it's a large value or below the mean because it's a smaller value than the mean. Z-scores are expressed as numbers with no units, and again we take those numbers out to 2 decimal places. We say that a data value is significantly low if its z-score is less than or equal to -2. In other words, data values that are smaller than 2 standard deviations below the mean. Or we say that the data value is significantly high if its z-score is greater than or equal to +2. So significantly high values are values that are greater than 2 standard deviations from the mean. If an individual data value is less than the mean, we'll see that the z-score calculation will give us a negative number, and if the data value is larger than the mean, we'll see that the z-score calculation will produce a positive number. Of course, if the data value is equal to the mean, then there's no distance between them, and the z-score will be 0 because the numerator of that calculation will be 0. Let's take a look at an example so we can use the formula to calculate the z-score. The question is, which of the following two data values is more extreme relative to the data set from which they came? So we have that the temperatures for adults have a sample mean of 98.2 degrees Fahrenheit. The sample standard deviation for the data set is 0.62 degrees Fahrenheit. And we want to see if somebody who has a temperature of 99 degrees Fahrenheit would be considered to be within the normal or expected range, or whether that 99 degrees Fahrenheit is so extreme that we would consider that to be a significant result. We'll also look at a separate scenario where the mean of the weight of coins, in this case quarters, the mean weight is 5.63930 grams. The standard deviation is 0.06194 grams. And we have a quarter that weighs 5.7790 grams. So we'll have to see how that weight compares to the mean and to the standard deviation to see if that is within what we would expect, or whether it is so far removed from the mean that we would consider that to be significant. So two separate calculations coming from two separate scenarios, but let's go ahead and practice with the formula. In the first case of temperatures, the mean temperature was that 98.2 degrees Fahrenheit. That is our sample mean, which is x bar. This is the value that we're going to be subtracting in the numerator. 99 degrees is the data value in question, so that is x. Here we see it in the numerator as well. And then in that example, the standard deviation for the temperatures was 0.62 degrees Fahrenheit, so that is what we're going to be dividing by. So the z-score for 99 degrees coming from that particular set is 1.29. This means that a person that has a temperature of 99 degrees Fahrenheit is above the mean by 1.29 standard deviations. In the second example, we were looking at the weights of coins, the weights of quarters. Again, we have the mean weight is 5.63930 grams. That's our mean right here, x bar. The quarter weight in question, the x value in question, was 5.7790 grams. We're going to subtract the data value and the mean in the numerator, and then we're going to divide that by the standard deviation given for the sample data, which was 0.06194. So that gives us a z-score calculation of 2.26. What this means is that this particular quarter is heavier than the mean of all the quarters in that sample, and in fact it is so much heavier that it is 2.26 standard deviations heavier than the mean. If you recall our range rule of thumb from the previous section, anything that falls more than 2 standard deviations from the mean is considered to be significant. In this case, a z-score of 1.29 would not be considered to be a significant result because it's within the 2 standard deviations. But a z-score of 2.26 falls outside of 2 standard deviations, so this would be considered a significantly high value. And that's what this slide pretty much summarizes. The standard deviation of 2.26, z-score I should say rather, the z-score of 2.26 would indicate that this particular quarter is significantly heavier. It's significant result, significantly high, whereas the body temperature of 99 degrees would not be considered to be alarming. It is within the expected fluctuation because that z-score was less than 2. Here's a visual for how we're going to determine if values are significant or not significant. I like to say not significant is to be expected. To me, those words make a little bit more sense. Because, of course, there is going to be some expected fluctuation of values, and there's a range for which we're not going to be surprised, and then there are values that are so far from where we expect them to fall that those are the ones that raise eyebrows and alarm us, and those are the significant values. Let's look at another example here. Among the earthquakes listed in dataset 24 in your ebook, one of the stronger earthquakes had a magnitude of 4.01. The magnitudes are measured on a Richter scale, and only earthquakes of magnitude 1.00 or higher are included. The 600 magnitudes in the dataset have a mean of 2.572. And again, these values are in your textbook. They're not included in this slide. The standard deviation for those 600 readings is 0.651. For this data set, the question is, would a magnitude of 4.01 be considered to be significantly high? To answer this question, we're going to need to compute the z-score for that x value. X is 4.01. Our x bar, our mean, would be the 2.572, and then of course the standard deviation is given as 0.651. Here we have the z-score calculation. Our data value in question is our x. Here is the given mean. We divide that difference by the standard deviation, and we get a z-score of 2.21. That means that this particular value is significantly high. Why? Because that z-score is more than our two standard deviations higher than the mean. So this would be considered to be a significantly high value. Let me back up to that visual so we can look again at where this falls. So the mean would be right here. That's the mean of the magnitudes, of the 600 magnitudes. The magnitude of 4.01 is about right here at 2.21 standard deviations. See how it falls in this green area? It would be considered to be a significantly high value. Now let's turn our attention to another measure of relative standing called a percentile. Percentiles are measures of location, and we denote them by using subscripts to the right of the capital letter P for percentile. So P sub 1, for instance, is the first percentile, P sub 2 is the second percentile, and so on. Percentiles divide a data set into 100 groups of equal size, each one having about 1% of the values from our data set. To calculate a percentile from a given data value, we will use the following formula. The percentile for the data value, which we'll call x, is equal to the number of values in our data set that are less than x, smaller than x. We're going to count how many of them there are. That is going to be our numerator. And then we're going to divide it by the total number of values in the data set, or our sample size, and then we're going to multiply that ratio by 100. So let's take a look at an example. The percentiles are actually quite simple to calculate. A little bit of work to count, but really the calculation is very straightforward. So here we have data values that come from wait times for the Space Mountain ride in Disney World. And we are asked to find the percentile for a wait time of 45 minutes. Thankfully, this data set is already sorted for us from least to greatest. If we travel through these rows to the right and then wrap around to the next row, they're already sorted from least to greatest. So we're looking at this number 45 and trying to find out what the percentile value is corresponding to this number. Well, if we look back at the formula, the numerator of the calculation says we have to count how many data values are smaller than 45. Well, we have, let's see, per row, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values per row. So we have 10 values in the first row, another 10 in the second row, another 10 in the third row, so that's already 30. And then if we go in the fourth row, that's 31, 32, 33, 34, 35, 36 of those values are smaller than 45. So I'm counting 36 values in this data set are smaller than 45. That's going to be the numerator. In total, we have 50 values, right? We have 5 rows of 10. So the denominator will be 50. And finally, we will multiply this result by 100 to get our percentile. So again, we have 36 values in our list that are smaller than 45. We have a total of 50 values in the list, and then we're going to multiply that ratio by 100, so we get a percentile of 72. Now that calculation wasn't bad at all, but what we have to focus on is interpreting what this tells us. What this tells us is that 72% of the values in this data set are smaller than the value of 45. So in other words, 72% of the wait times for this ride are shorter than 45 minutes. Notice that a way of writing this a little bit more concisely is that we can say that P sub 72, P sub 72, or the 72nd percentile is equal to 45. Now let's look at some labels that we're going to refer to as we look at our next calculation, because we just looked at how to go from a data value to its percentile. We now want to look at a procedure for going from percentile to a data value. Again, n is going to represent our sample size, which is the total number of values in the data set. K is going to represent the percentile being used. So think about those subscripts. In the last slide, we were looking at the 72nd percentile. We had P sub 72. This is that subscript. K is going to be the percentile value. K is that subscript. Capital L is going to be used to locate the position of a value. So when we say, for instance, that L is 12, we're saying that L is the 12th value in a sorted list from least to greatest. So L is a position. It doesn't tell us the value itself, it tells us where it is located in a sorted list. And then finally, as we said earlier, P sub K is going to refer to the kth percentile. So K is a subscript. For example, P sub 25 refers to the 25th percentile. This graphic doesn't show up very well in this slide because the print is rather small, but it is in your ebook as well. And of course, you can pause the video and expand your screen to see this a little better. Again, if we're going in the opposite direction, if we're going from a percentile back to finding what data value it corresponds to, this is going to be the procedure to follow. First, you're going to always start by sorting the data from least to greatest. Second, you're going to find the location of the data value that we're trying to find. That location L is going to have the following formula. You're going to take the percentile that you're trying to find, so that's going to be given in this case. Let's say you're looking for the 25th percentile, then K would be 25. Divide by 100, and then multiply by the number of values in your list, which is n. And you could end up with a whole number, but you also could end up with a decimal. So if you have a whole number, then what you're going to do is you're going to go, you're going to go halfway between the number in that position, in the nth position, and the next value in the list, which is the L plus first position, and then divide by 2. We're going to see an example of this in a bit, so if it doesn't quite make sense now, don't worry, we will go through an example to illustrate this. However, if L is not a whole number, so you get, for example, L is 12.5 4. Then what you're going to do is you're going to round L up to the next whole number, always up, regardless of what the decimal values are. For example, if we got 12.4 for L, we would still round that up to 13, and we would not follow the traditional rounding rules, always to the next whole number. And then the percentile value would be in that position. All right. It's always better to look at concrete examples, so let's take a look at one here. Here are 50 wait times. Same example as we saw in the previous slides, looking at the Space Mountain ride in Disney World. And we're asked to find the 25th percentile. Notice that this is a different question than what we saw previously. The previous example said find the percentile for a wait time of 45 minutes. So that question was worded so that we were looking at a data value and trying to find what percentile that corresponded to. This is a different question, and it goes in a different order. It's saying we want the 25th percentile, we just don't know which data value that is. So we start out knowing the percentile, and we have to work backwards to find what data value that corresponds to. Well, let's use the formula that we saw in the previous slide. First of all, we know that K is 25. We know that our sample size is 50 because there are 50 values here. So we're going to divide 25 by 50. We're going to divide 25 by 100 and then multiply by 50. We'll see that in the next slide. 25 divided by 100 multiplied by n, our sample size 50, gives us 12.5 for L. Remember, L is not a value, L is a position. So we got a position that is a decimal, which means that we're going to round up to the next whole number. In this case, we're going to look at what value is in the 13th position in the sorted list. So again, there are 10 values per row, so we know this right here would be the 10th value, this is the 11th, 12th, this is the 13th value in the sorted list, the one here circled in red. So the 25th percentile would have a value of 25 minutes. Alright, now let's take a look at quartiles. Quartiles are another way of talking about relative standing. So quartiles, and there are 3 of them, quartiles divide our data into 4 equal parts, each one having approximately the same number of data values. Now the reason we don't have 4 quartiles and we only have 3 is that the 4th quartile is the same as our maximum value. So there are still 4 sections, but we only talk about the 1st, 2nd, and 3rd quartiles. What would have been the 4th quartile, we have a better name for that, which is the maximum value. But again, what quartiles do is they divide our data list into approximately 4 equal parts, each one containing about 25% of the values in the group. So the first quartile contains 25% of the values. It is synonymous then with the 25th percentile. Why? Because the 25th percentile is larger than 25% of the values in the list. The other 75% of the values would be higher. The second quartile has another name. It is known as the 50th percentile. Why? Because it has 50% of the data values that are smaller, 50% of the data values that are larger approximately, and there's a third name for it. We know it as the median. Why? Because the median is the middle value in a sorted list. So there are 3 names for the exact value. The second quartile is the same as the 50th percentile, which is the same as the median. Finally, we have the third quartile, also known as the 75th percentile. We know that it is higher than 75% of the values in the list. That means that the other 25% is higher than P75. And as we said earlier, there is no fourth quartile because we would know that as the maximum value. And of course, the maximum value is larger than all the other values in the list. A caution here is that just as there is no universal agreement on how to find percentiles, there's also no universal agreement on how to calculate quartiles. So there might be some small differences depending on whether you're using a calculator, a manual formula, Excel, for instance, SPSS, or other computer programs. They won't vary very much, but you might see some slight differences. In this course, we're going to be consistent, though, with the formulas that I've presented, so we should not have different values. Let's talk about how to summarize some of these calculations and how to use them to really inform us about what's happening with our data set. We have something called the 5-number summary, and basically it consists of 5 values as follows: the minimum value, the maximum value, and then the 3 quartiles, first, second, and third quartiles. So we have minimum value, first quartile, second quartile, which is the same as the median, third quartile, and then the maximum value. If we were to calculate these 5 numbers and then use them as a group, we can actually make a lot of conclusions about what's going on with the data set. It gives us a measure of center, it gives us a measure of spread, it gives us a sense of where there might be possible outliers, and it also can give us a sense of shape. So these 5-number summaries actually are very useful because they can shed light on many of the characteristics that we want to know about for a numerical set of data. Let's go back to the same example we've been working with the 50 wait times for the Space Mountain ride in Disney World. In this data set of 50 values, we can quite easily find the 5-number summary. Of course, 2 of those values are super simple. The minimum value would be 10. The maximum value is 110. The median would be the next calculation. The median would be right here between these two 35s. We have an even number of values, so we would have to take the mean of the 2 competing middle values, which happen to match. So the median here would be 35. So again, minimum and maximum are pretty easy to identify. We already talked about the median being the tiebreaker here between these 2 values, which happens to be 35 itself. Now, lastly, we would find the first and the third quartiles, and let me explain how to find them manually quite easily. If we first find the median, which we did right here, it splits this list into 25 values on the lower part and then 25 values in the upper part. In other words, right here where my cursor is, there are 25 values that would fall lower and 25 values that would fall higher. If we think about those 2 chunks as being 2 separate lists, find the median of the lower 25 values, and that is going to be your first quartile. Then, if you look at the list that has the 25 higher values, and you were to find the median of that list, you would find the third quartile. So think about it as you're folding a paper in half, and then you're folding that in half again to get four rectangles. You first cut the list in half by finding the median, and then you cut each one of those halves in halves again to find the first and the third quartile. So finding the median of the lower half and finding the median of the upper half will give you the first and the third quartiles, which in this case are 25 and 50. So the 5-number summary for this example consists of these 5 numbers. Minimum value is 10, first quartile is 25, second quartile, or also the median, is 35, third quartile is 50, and the maximum value is 110. Now, I said earlier that these 5 numbers are going to shed light on measures of center and variation and possible outliers and shape, and it doesn't quite seem like those 5 numbers did that for us, but they will. We just have to put them into a graph, something that our eyes can glean some light from. And that is called a box plot. So a box plot is essentially a graphical representation of that 5 number summary. What we're going to do is we're going to draw a number line, and on that number line we're going to label the 5 numbers from the 5 number summary, and rather than just looking at those 5 tick marks on the number line, we're going to build a box and we're going to build some arms, and we're going to look at that in a much better way. So first we draw the number line, we label the 5 numbers from the 5 number summary, and then the 3 middle numbers, so the first quartile, the median, and the third quartile, we're going to build a box around them, a 2-dimensional box hovering over the number line. Then we're going to draw some line segments from that box, reaching out to the minimum value and then reaching out to the maximum value. So it looks like a box with 2 arms. And that is what a box plot is. So again, looking back at our 5 number summary for this example, minimum value was 10, first quartile was 25, the median is 35, third quartile is 50, maximum value is 110. We are going to put a box around these 3 numbers, Q1, median, Q3. We're going to put a box around these 3, and then we're going to draw some arms reaching out to the left all the way to 10, and then reaching out to the right all the way to 110. So here is what that box plot would look like, and I'm going to move this a little bit so you can see. Down here is our number line, labeled. The value of 35 would have a tick mark right around here. Q1, the value of 25 would have a tick mark right around here. 50 would be right around here. And what we're going to do is we're going to draw this 2-dimensional box, this rectangle, hovering over where those labels would have been. Now, to the left of the box we have Q1, to the right of the box here we have Q3, and then we're going to add this little line segment where the median is. Finally, we're going to draw these arms that extend out to where the minimum value would be. Notice that that's where the 10 would be on the number line. Put a little bar there, and then we're going to extend an arm all the way to the right to that maximum value of 110. So what you see here in blue, that is our box plot. Now, my promise to you was that we would be able to glean some light onto measures of center and variation and also possible outliers and even shape. So here's how we do that. First of all, because the median is labeled, median is one of our measures of center. So we would say that this data set is centered at 35 minutes because that's the median. In terms of spread or variation, that's what this box pretty much tells us. It tells us that from that center, most of those data values, the middle 50%, extend between 25 and 50. So this gives us a measure of variation. The wider these boxes are, the more spread there is. The narrower these boxes are, the less variation there is. Now let's look at possible outliers. You see that to the left we have somewhat of a short arm reaching out to the minimum value, but to the right the arm is really long, and it seems like it has to stretch a lot further to reach that maximum value. That means that that value might be considered to be extreme, or even an outlier. Certainly would make us question why that value is so long or so high. By the way, I'm calling these arms In statistics, we refer to these as the whiskers because a box plot is also known as a box and whisker plot. And lastly, I think this also gives us a sense of shape. If we were to think of this as being a histogram, we would expect there to be pretty tall bars right around here, and then a little tail over here to the left, but a really long tail all the way here to the right. And so on the next slide, let's see if we can make a connection. When you're looking at these box plots, our box plot, even though the numbers are different than what we see here, looks more like this, where it's got a shorter whisker to the left and a much longer whisker to the right. This is the histogram that corresponds to that box plot. We see that if we were to describe this shape, we would say it is skewed to the right or positively skewed. That longer stretch to the right is represented by this longer whisker to the right. So when you have a much longer whisker in one direction, that would indicate the direction of skewness.